Bismillah ar-Rahman ar-Rahim. Good afternoon, everyone. Today we'll try to do a good summary to this article, current induced electric resistance in this component. The scientist was Rebello and another one. At first, let me do a simple review related with what is the resistance, what is the meaning of the resistivity, electric resistance, what the relation between them. Let's keep going to take a look to the next slide. Here, at first, we will talk about the resistivity. It's an important element, important factor in the electric circuit. Actually, it has advantage and disadvantage at the same time, because that's interesting topic to any physics, researcher. At first, let's talk about the advantage to this to any resistor, like we know, because when you use copper wires of copper, something like that, because this phenomenon will use some amount of current by heating to the surrounding place, to environment. Our loss will be like that. Current, we will lose current, and this current will convert to heating. At the same time, let me talk about the advantage to this phenomena. We can use it to protect our electric devices, speaker, radio, anything. We use it in the electric circuit. We will use another resistance, appropriate resistance with this device to can protect our devices from heating, from damage, many things like that. Let me keep going. Here, lower resistance make the current flow less difficult, and with more resistance makes the current flow difficult than less resistance. Because that we use copper, it has a low resistance. We don't have in our planet material with zero resistance, but we will talk by using benefit subjects, because that we selected the copper with less resistance. It has a benefit because that it is not cheap, it's expensive metal. With why? Because it has less resistance. We can use it with less losing of current, with longer distance. Let me take a look to this slide and keep going. But with circuit, as advantage, like I said before, we use this to protect our device. All of these slides, and the next one will be talking about something like review to important information. After that, we will go deeply to this article. Electric resistance, like we know, it's a huge change in the resistivity to the simple or a simple. And at the same time, it's analogous to friction in a mechanical system. They both, electric resistance, resistivity, both convert energy to heat and dissipate it to surrounding environment. Now, why the electric resistance exists? Basically, electric resistance device resistors are interested into circuits, but like I said before, it has advantage and a disadvantage at the same time, like any material. But we use this disadvantage to protect our device. That means we will save more money, and many interesting phenomena because it's very interesting topic. Some metals are more resistant than others. Let me take example or comparison between the nickel chromium. We use it with some amount of current. It's heating and start to close rate. But when we use a copper, the situation is different because it will not glow red but trip your circuit breaker. Like I thought, most of the resistance, the wire inside it, was made from the nickel chromium. Here, let's talk about the function between the resistance and resistivity. Actually, the resistivity equal resistance times square of current. And if we talk about, let me start by using the Ohm's law. I equal V equal IR, the voltage equal current times resistance. That means current equal what? Equal voltage divided on resistance. When the current equal 0, so when the resistance equals 0, let's say it's a very perfect metal and it doesn't has any resistance, what we'll do? That's mean from Ohm's law, I equal infinity, because like we know, any amount divided on 0 equal infinity. What that's mean? That's mean it's threads on our electric circuit, because the current will flow suddenly, and at the same time the electric power will start to heat, and maybe explosion, maybe we will face some damage in our circuit. It is very dangerously, like I said before, high current, and it can burn. Like I said before, resistivity equal resistance times square of current. High resistivity of conductor metals cases high resistance. That's mean the relation between all of them. When we note some increasing in the resistivity, there's another side we will note increasing in the resistance. Now, here, let's take some notes about this article. This is the first slide, talks about the article. In this article, Rebello used two kinds of current, DC and pulsed current. Here, pulse current, and here we noted decreasing in the electric resistance in this component as a function of temperature and electric magnetic. What that's mean? That's mean here electric resistance as a function to all of the temperature and electric magnetic state, magnetic field. Sorry. The peak voltage decreases at threshold current in magnitude and shifts to increased current with high magnetic field. Let me say that again, the peak voltage decreases at what? At threshold current in magnitude and shifts to increase the voltage with high magnetic field. Note, while the Joule heating assists electric resistance in the high DC current regime, the nonlinearity in the pulsed current sweep and the resistivity switching between high and low value. We will explain these slides deeply at the next slides, when we will use the diagram to explain this phenomena. Include by controlling the width and period of pulses. Sorry. Here, let's take a look about the main form to this manganese. rare earth 1 minus X, the construction, and alkaline with X concentration, manganite, 3 atoms of oxygen. Here, the both of the alkaline and rare earth are sensitive to the external electromagnetic pressure, X-ray radiation, and electromagnetic. In particular, compounds which show coexistence of isolating, charge ordering, and ferromagnetic states show variation in the resistivity by the application of such external stimuli. We will talk about the stimuli in the next slides, which kind we have, and some simple idea about the stimuli kinds. Here, we noted an important thing from this article. At more than or approximately 700 voltage, this huge voltage able to switch isolating charge ordering state to ferromagnetic state, metallic ferromagnetic state. Due to what? Due to the competition between charge ordering and magnetic ferromagnetic state, and cases a huge decreases in the resistivity. That means voltage, high voltage like that can switch the isolating charge ordering to FM, and after that, at the same time, we will note huge decreases in the resistivity. Here, the first diagram, the first plot, it's temperature resistivity plot. We have different amounts of current. Actually, at first, the amounts of current with no magnetic field, magnetic state. First amount of current 1 milliampere, 10 milliampere, 20 milliampere, and we will note the difference between them. At first, with no magnetic field, with 0 Tesla. Here, all of the change started from approximately 10 Kelvin. Here, when the sample is semiconducting at natural, this equation is derivation of resistivity divided on derivation of time smaller than 0. Significant joule heating at low cooling can lead to decrease in resistivity. That's mean decrease in the resistance, because like I said before, resistivity equal R, resistance time square of current. After isolating metallic temperature, let's take a look. Here we have at 0 Tesla, we have 3 different amount of currents, like I said before. At the weaker one, at 1 milliampere, we have hysteresis phenomena when cooling and heating the material at the same weaker current 1 milliampere. At first, here, it's recorded a huge amount of resistivity at isolating metallic temperature at less than 70 Kelvin, and after that recorded less than resistivity less than 1000 ohm centimeter with approximately 75 Kelvin at the same amount of current 1 milliampere. Here, what does mean? That means the resistivity is decreasing. All of these at the cooling period at less than isolating metallic transition. Here, it's important to note a large amount of current, approximately 30 to 100 milliampere, can do what? can lead to decrease the resistivity, and what that means, increasing the electric resistance, because between the resistivity and electric resistance, a reverse relation. Let's take a look about 30 and 100 milliampere. This phenomena has happened. I mean, the resistivity started to decrease and electric resistance started to increase. Here, let's come back to 0 Tesla. Like I said before, the resistivity at 1 milliampere, it's bigger than the resistivity at 20 milliampere. That means with increasing the current, the resistivity is decreasing. Our conclusion, we take it from this diagram. At 1 milliampere, the isolating metallic transition is approximately 60 Kelvin, and these are when cooling or heating. One from them, cooling or heating, the temperature is approximately 60 Kelvin, and after cooling it or heating it, I don't know, from this point, it's less than 100 Kelvin. At the same time, the resistivity is decreasing. Here, the hysteresis started to disappear at 150 Kelvin, and not approximately, sure, it's disappear. We don't have any hysteresis phenomena anymore at 200 Kelvin. Here, the hysteresis and the temperature resistivity disappear at these two different amounts of current. I mean, at 10 milliampere and 20 milliampere, the situation is different. We don't have any more hysteresis phenomena. But at the same time, that means when we don't have any magnetic field, we have just hysteresis at the last amount, at the least amount, the weaker amount of current. It was equal 1 milliampere. But at the other, when current start to grow up, we don't have any hysteresis. Here, the situation is different when we have a magnetic field. Let's say we increase this magnetic field to be equal 5 Tesla. The situation is different. We have some change, but negligible change when we do comparing with the 0 Tesla. Is almost negligible, between 100 Kelvin and less than 125. But let's take a look, because we are researchers, why when we have a magnetic field, the resistivity drops. The resistivity starts to decrease. Like I said before, at 1 milliampere, it was more than 10 milliampere and 20 milliampere. This, I'm talking about the current. And at the same time, when you use 1 milliampere and 20 milliampere, like here, 1 milliampere and 20 milliampere, with increasing the magnetic field, the results about the resistivity is started to decreasing. Here, after take some information from another article on this link, the magnetic field depends on some things like resistivity and theorem power. That means some relation between the magnetic field and resistivity. Show their reversible relation between the resistivity and magnetic field. At the same time, irreversible behavior between the magnetic field and resistivity, but near from isolating metallic transition. That's mean two different behaviors. That's dependent on near or far from the isolating metallic transition. When be far from isolating metallic transition, the relation between them is reverse. That's mean when increase the magnetic field, the resistivity will start to decreasing, depending on weather of the sample. And let's focus on this note, which indicates the electric bond structure near from metallic transition is magnetic history dependent. Here's important little bit, which indicates the electric bond structure near from metallic isolating temperature magnetic history dependent. All of this information from this link. Here, application of an applied magnetic field of sufficient magnitude can lead to what? Here, it's another part of solution about the previous question. Lead to collapse of what? Collapse in which part? In charge ordering, Fermi level, the last one, melting of isolating charge ordering to ferromagnetic material, ferromagnetic, because that we noted some decrease in resistivity when the magnetic field is increased, because application of applied magnetic field sufficient magnitude can lead to collapse in charge order, Fermi level, isolating charge order to FMM. These 3 points are important too. What is the T surface? T surface is the temperature of the surface of this sample, and it's different from sample to another. Magnetic hysteresis occurs when an external magnetic field is applied to a ferromagnetic such as ion, even when the field is removed. Here, let's focus a little bit. When the field is removed, what will happen? Part of the alignment will be retained. The material has become magnetized. The magnet will stay magnetized ad infinity. Here, it's important. It's the Nd0 plot. I take this picture from the mine plot, the previous mine plot. Here, the situation is different. T service, not like this normal T. Here to the T service to this simple. And resistivity, the T service resistivity. Here, the author, the scientists, just decided to flow just two currents, 1 milliampere and 20 milliampere, and calculated another results, what it happened. Here, at first, at 1 milliampere, the same situation, the resistivity, it's more than at 20 milliampere. We have hysteresis between, we don't have hysteresis here, I'm sorry. The isolating temperature is approximately 75, but at 20 milliampere is 100 Kelvin. That's mean at 20 milliampere, that's more than more than at 1 milliampere. Here, even though the base temperature recorded by this technique at 10 Kelvin from here, 10 Kelvin. This suggests a strong evidence for Joule heating in the sample at higher current magnitude. Here it's important plot. Actually, the scientist plotted this diagram by plot the IV curve and plot this different curves, the butterfly curves between reverse current and positively current by using three different amounts of current, 0 to 20 milliampere, minus 20 milliampere to 20 milliampere, and after that from positively 20 milliampere to minus 20 milliampere, because that we have this butterfly behavior, butterfly phenomena. Let's take about it by take one after one, and after that calculate the current with the T service to these samples. Like I said before, we have three different amount of currents. Let's take out first at the found strong non-line. Let's talk at first on the IV curve or IV characteristics. Here, found a strong non-linear IV characteristics at current less than 20 milliampere. What is the less than 20 milliampere? That means at this period of current from zero, from less than 20 milliampere, go back to 0 milliampere. We have non-linearity behavior like that with different amount of temperature, start from 30 Kelvin, 50 Kelvin, 100 Kelvin, and we know something, when it start to continuously increase the current, this non-linearity will be weaker and weaker to be something like line or lines. From non-linearity behavior convert to linearity behavior. When the voltage increasing linearly with current, what we'll do, approximately until a critical point, the voltage will increase, and after that will start to decrease. But about the threshold current, the voltage starts to decrease. After these critical points, the voltage amount start to decrease. Now, when the current is swept up from zero, from 0 to 20 milliampere at 30 Kelvin, this first one, the first ball, the voltage shows a sharp increases at lower current, like I said before. At lower current, flowed by a peak around 10 milliampere, is less than 10 milliampere, before decreasing at high current. That means the voltage will increase with low current and decrease with high current, amount of currents. Now let's talk about from 20 to minus 20 milliampere and reverse that from minus 20 milliampere to 20. The IV curve tracks different paths like that, the butterfly curves, butterfly phenomena. Anyway, after a full cycle, a clear hysteresis is observed in the IV characteristics. The IV characteristics at other temperature also exhibits NdR. I will define what that means, but it's not interesting to my topic because I'm focused on the electric resistance, focus on any interesting phenomena inside there, what the authors didn't explain about some questions, something like that, because that NDR or another technique uh, to take scanning to determine some amounts, it's not important to me. At high temperature, as can be seen in the figure here, at high temperature, like seen in the figure, what it's happened. The non-linearity behavior converts to be linearity behavior. And here is a network detection and response solution. It's a solution are designed to detect keeper threads on the corporate network using. Here, the IV characteristics is almost linear, where at 250 Kelvin at a high amount of current and above, and more than 250, actually from 200 start to be linearity behavior, and more than will be like that. Non-linearity in the IV characteristics below 150 Kelvin. Below 150 Kelvin is non-linearity behavior, but after that starts to be non-linear, starts to be linearity behavior. That's mean when increasing the temperature here, when increasing the temperature, the voltage is increasing, decreasing the temperature, increasing the voltage. From here, 30 Kelvin, the voltage, it was more than the voltage at 50 Kelvin. And keep going. Now let's take a look to the inset plot. I take this picture from my previous picture plot. The inset at the bottom shows the change in the T service of the sample while sweeping the DC current. Like I said before, we have different amounts of current, 30, 50, until 250. At IV, until 150, the behavior, it was non-linearity behavior, and it was very clear. Here, let's take a look after or above more than 150 or started from 150 at IV curve, then the behavior converts to be linearity behavior at the same time. Less than 150 non-linearity, 150 and more than, it was linearity behavior. Here, the inset, like I said before, let's take a look about 150 and more linearity with T service. Here, the situation is different. This curve explains the relation between current and the T service. The previous one between the I with V at y-axis. Here, linearity behavior, non-linearity behavior, some decreasing from the base temperature and increases to be more than. Let's take the white ball, start from 30 Kelvin and increase to be approximately 100 Kelvin. Or let's talk by take the right side from 0 at 30 Kelvin. With increasing the current, the T service will increase to be approximately 100 Kelvin. Let's take the red ball, this one, started from 50 Kelvin the base temperature and increase to be more than 100 Kelvin, with increasing the current from 0 to 20 milliampere. Now, actually, let me say something. This lecture is longer than the previous one because that I will make this lecture to be 2 parts. This is the first one, and after that I will start to record the second one. This will be the last slide, and after that I will finish this video to start recording another one. It is found that the observed nonlinearity in IV characteristics below 150 Kelvin is a combined. Here is very important slide, maybe important than the other. Nonlinearity in IV characteristics below 150 Kelvin. What does mean below 150 Kelvin? That means this side, less than 150 Kelvin. And at the same time, that means the white one, red, blue, until this triangle. 1, 2, 3, until the blue triangle. It's all of these are less than 150 Kelvin. Here below is accompanied by a significant increase in the T of the sample and the surface temperature. Here, with all of these, some increase in the T of the temperature. That's like I said before, when flow the current, the base temperature, like here, started from 30, finished to 100 Kelvin approximately. With increase the current, the temperature, it was increased. At the same time, for example, by take the rate one, start from 50 Kelvin, the base temperature, and increasing with increasing when the current is increasing to be more than 100 Kelvin. That's mean an increase in the T of the sample. Thank you about your watching or listening. Have a good day and see you in the next lecture.